Now, naming the coordination compounds can be a bit tricky, but here's some general guidelines to help you. First of all, determine the name of the non-complex ion, so the things that aren't bound to the metal ion. Then you're going to need to determine the ligand names and list them in alphabetical order. Then we need to determine the name of the metal cation. Fourth, name the complex ion by naming each ligand alphabetically, adding a prefix in front of each ligand to indicate the number found in the complex ion, and then follow with the name of the metal cation. Write the name of the cation followed by the name of the anion, so it's always positive and negative. I can kind of think about saying this like, give me the good news first and then the bad news. So give me the positive and then give me the negative. So here we have two example complexes to help us understand this. So remember, this entire thing here is the coordination compound, but the complex is identified by in the brackets. So this is telling me there are three oxalate ligands bound to this aluminum. So the name is potassium trioxaloaluminate 3+. So the 3 tells me the oxidation state of the aluminum. Each oxalate ligand has a -2 charge. Each potassium has a +1 charge. So there are 3 of those potassiums, so it's a total of +3. And then there are 3 oxalates, so -6. So to balance out the charges, the aluminum has to be a +3. So the parentheses, we have Roman numerals 3 to indicate the oxidation state of the aluminum. The tri tells me that there are 3 oxalate ligands, and the ligand comes before the aluminate. Also notice too that this name has 2 words associated, so there's a distance between the potassium and the trioxaloaluminate. This tells me that the potassium is not bound to the aluminate. The potassium is my counter ion. Now also too, notice that even though there are 3 potassiums here, I don't write that there are 3 potassiums here. It's redundant information, because if I know that the aluminum is 3+, and there are 3 oxalato ligands that are each -2, that tells me by deduction that there have to be 3 potassium ions to balance out the charge. So rather than writing like tripotassium or anything like that, I just leave that out. So let's try for this cobalt complex. Here we have the cobalt complex, which is the cobalt with the 2 chlorides bound to it and the 2 ethylene diamine ligands bound to it. So that's the complex. The coordination compound is the whole entire thing, including the sulfate counterion. Notice the sulfate is not written inside the brackets. That tells me that it's not bound to the cobalt. So if I were to write the name of this, I have the chlorine and I have the ethylene diamine. Chlorine comes before ethylene, C comes before E in the alphabet, so the chlorine is listed first. And there are 2, so it's a di to indicate 2, so it's a dichloro. So we change the name of the chlorine to chloro. This means that there are 2 ethylene diamine complexes, and the cobalt has a 3+ oxidation state. The ethylene diamine is neutral. Each chloride is a -1, but there's 2 of them, so it's a -2. The sulfate has a -2 charge. Let's do this another way. So the sulfate has a -2 charge. But one of the things here you have to be careful of, there's a subscript here. So each one of these complexes has a +1 charge. So if this complex has a +1 charge, let me just draw this out very quickly. So cobalt, one amine, two amine, and a chloride, and a chloride. So this whole thing has to have a +1 charge, and there are two of these complexes, as denoted by the subscript here. So the overall charge is +1. Each chloride is a -2. So the cobalt itself has to be a +3. So the entire name is a dichlorobis ethylene diamine cobalt 3 sulfate. So this is the cation first, and this is the anion. And again, it's separated by a space because it's two words, because you have a cation and an anion. Now, one other thing that I forgot to mention with the trioxylato-aluminate, this complex here, because the potassium has a positive charge and this aluminum complex has an overall -3 charge, to indicate that the alumina is part of an anion, we change the ending of the name to -ate. So rather than aluminum, it's an aluminate, because the aluminum is part of the anion. So this is the anion, and this is the cation. Now, the rules for naming transition metal complexes can get very tricky. That's why you only have to be able to recognize the correct name of a transition metal complex, since we do the naming by multiple choice exams. Here are some common ligands. So the anion, notices the bromine is a bromide, but when it's bound to a metal complex, we change the name. So the bromide becomes bromo, the chloride becomes chloro, hydroxide becomes hydroxo, cyanide becomes cyano, nitrite becomes nitro, oxalate becomes oxalato. So we change the name of the anion once it's bound to the metal and becomes a ligand, and it has that O form. Some other common ligands, these are neutral molecules. Water is an aqua ligand. Ammonia becomes amine, and the amine has two M's. Carbon monoxide becomes a carbonyl. Ethylene diamine, which is abbreviated EN, becomes ethylene diamine. So it stays the same. And the ethylene diamine tetraacetate becomes ethylene diamine tetraacetato. So now that we looked at how to name some of these compounds, let's look at how to classify isomers. Now, isomers are two or more molecules or ions with identical formulas. The first thing is we're starting to classify isomers. The first question we ask ourselves are the bonds between the atoms the same? If yes, these are called structural. If yes, these are stereo or configurational isomers. And if each is identical to its mirror image, then these are going to be diastereomers or geometric isomers. But if they're not, they're called enantiomers or optical isomers, and these are chiral or non-superimposable mirror images. But let's say we go back to our original question, and the bonds between the atoms aren't the same. These are then called structural or constitutional isomers. And there's several different types of these constitutional or structural isomers. The first is the ionization isomer. Then there's a linkage isomer. There's also a coordination isomer, and there are also hydrate isomers. And in the next couple of slides, we'll actually go through some of these different types these different type of isomers. So our first type of isomer that we're going to look at, which is a structural isomer, is the ionization isomer. And basically it gives different ions when dissolved in solution. Ionization isomers occur when a ligand or a counterion in a compound change place. So let's say we have this cobalt complex and there are 5 amines, 1 bromo, and 1 sulfate. And there's another compound that has the exact same composition, but one is red and the other is red-violet. So if they've got different colors, there has to be something different about them, even though they contain the exact same atoms. Well, in this red-violet form, if I add barium to it, barium sulfate will precipitate. So what that tells me is that the sulfate isn't bound to the cobalt. It's not part of the complex. So if the barium sulfate precipitates and the sulfate's not part of the complex, then the complex has to be the cobalt complex with 5 amines bound to it and 1 bromo ligand. So this compound has a red-violet form. But the red compound, if I were to add silver to it, silver bromide would precipitate out of solution. And silver bromide tells me that the bromide, or the bromo, is not bound to the cobalt. So it's not part of the complex. It's actually a counterion. So if the bromine is not bound to the cobalt, then that means that the sulfate is. So the cobalt complex has 1 sulfate ligand and then the 5 amines bound to it. And the complex has an overall +1 charge. So it's this difference bond here in the red form that gives it the red color. And the bromine here causes this complex to be red-violet in color. So there we have ionization isomers. Here the counterion was the SO4 2-, and here the counterion was the bromide. And we were able to determine what was the counterion by precipitating it out with another added cation. Now linkage isomers are the same ligand, but they're bound through different atoms. So here we have 2 different cobalt complexes with the same ligand, but in one, this is the nitrito form, so the nitrite is bound through the oxygen. So the oxygen is attached to the cobalt here. But in the nitro form, the nitrogen is bound to the cobalt. And this complex is yellow in color, whereas the other complex is red. So here we have a picture of that compound in the red form, and here we have a picture in the yellow form. And so the difference is the linkage isomer and how that nitrite ligand, so NO2-, is bound to the cobalt. This is what's called an ambidentate ligand because it can bind in 2 different ways. It can either bind through the oxygen, which has lone pairs, or it can bind to the nitrogen, which also has lone pairs. Coordination isomers, this is where the total ratio of ligand to metal ions remains the same, but the ligands attached to a specific metal ion change. Here we have an example where we're using the empirical formula that there's always a ratio of 2 amines to 1 platinum and 2 chlorides to 1 platinum. You can have this platinum complex where it's just 1 platinum and 2 amines and 2 chlorides. And this is actually a very famous drug. It's a very famous anti-tumor drug called cisplatin. Or you could have these 2 complexes that balance each other's charge, where one is a platinum with 3 amines bound to it and 1 chloride. And here we have a platinum with 3 chlorides and 1 amine. So this would have a +1 charge, and this would have a minus charge. So you have to have these two complexes to balance out each other's charge. But then notice there's still always a ratio of 2 amines to 1 platinum. So there's 2 platinums, so platinum 2, and then NH3, there's 3 here, 1 here, so a total of 4, and a total of 4 chlorines. Oops, 4 chlorines. So if we reduce this down, we still have the same ratio. Or we can have Magnus's green salt. So this is a platinum, this is a 2 plus complex, and this is a 2 minus. So again, there's still a ratio of 4 amines to 2 platinums and 4 chlorides to 2 platinums, so you still get the same general ratio. So these are all examples of coordination isomers. Hydrate isomers are where you have the proportion of coordinated water molecules that differ between the isomers. So if we're, in this example, we have chromium 3, chromium trichloride with 6 water molecules. There is the violet form that has 6 water molecules bound to the chromium, and you have 3 chloride ions balancing out the charge. There is a light green form that has 5 water molecules bound to the chromium with 1 chloride bound. And then there is a dark green that has 4 waters and 2 chlorides bound to the chromium. And you have the chloride counterion. But this is a dihydrate complex. This is a monohydrate. And this doesn't have any water of hydration. It just has 6 water molecules bound to the chromium. So if you were to dissolve this in solution, this chromium complex here in the violet form, this would produce a total of 4 ions in solution. The chromium complex and the 3 chloride ions. In the light green form, this would form 3 ions when dissolved, 1 from the chromium complex and 2 from the chlorides. And in the dark green form, there would only be 2 ions in solution. So there'd be the chloride and then the chromium complex itself. We could actually use the conductivity of the solutions to distinguish between these different complexes. So with 4 ions that are formed, this violet form should form a solution that conducts electricity better than the 3 ion, and that's even better than the 2 ion complex. We can also use UV vis spectroscopy to look at the different colors between these two. But a chemical test that we can distinguish between these would be, what about if we added silver plus to these? If I add silver, the chloride counterions will combine with the silver to make silver chloride. And silver chloride is very insoluble and it precipitates out. And what I can do is I can measure out how much silver was added and the amount of silver chloride that was formed. I could calculate the number of chloride ions. So it would take 3 equivalents of silver to precipitate all the chloride ions in the violet form. It would take 2 equivalents to precipitate all the chlorides in the light green form. And it would take 1 equivalent of silver to precipitate all the chlorides in the dark green form. Geometric isomers are stereoisomers that differ in the spatial orientation of the ligands. So the bonds are the same, it's just how they're arranged about the atom are different. For example, cis and trans isomers in square planar complexes. So we have a platinum metal center and 2 chloride ligands. But in this case, on the left-hand side, this is the cis isomer. So cis means that they're on the same side, but in the trans, they're on opposite sides of the platinum complex. So cis, they're on the same side, trans, they're on the opposite. So you can get cis and trans isomers for square planar complexes. You can also get cis and trans isomers in octahedral complexes. So this would be the cis isomer for this octahedral complex, and this would be the trans isomer where they're on opposite sides of the molecule. Another type of geometric isomer is the FAC and the MER isomer. So the FAC is an abbreviation for facial. So if you think about this as being an octahedron, so an octahedron has 8 faces. The chloride atoms here are all on the same face. So they're all in the form of this triangle here. So these are FAC isomers. All 3 ions line up on the face of the tetrahedron. All three ligands line up on the face of the octahedron. But the MER stands for meridional. Meridional. So that's where they get the MER. So think of them all being the same line, like the prime meridian that goes through a globe. So these all lie within the same plane as the central metal ion. So here you have 2 axial ligands and 1 equatorial ligand. You're only going to see FAC and MER isomers with octahedral complexes. These are just other examples or other illustrations to show you the difference between cis and trans. So this would be the cis because they're on the same side. These are also cis isomers because they're next to each other. They're 90 degrees from each other in the octahedral complex. But here these would be trans because they're on opposite sides of the cobalt. Again, just another illustration showing you the FAC isomers. So these are on the face of the octahedron. These all lie within the same plane of the central atom. This is the MER isomer, the meridional isomer. And there are also geometric isomers or diastereomers. Optical isomers are stereoisomers that are non-superimposable mirror images of each other. So example would be your hands. Your hands are mirror images of each other, but you can't overlay them so they overlap completely and they completely cover the other. They actually look different. So this isomer here is the delta isomer. So if you imagine putting a mirror in between these two, you would see this image in the mirror. But if I try to overlay this lambda version with the delta, I would have lines going here and the lambda version, but not here. So they aren't superimposable. You can't overlay them exactly to exactly cover up the other one. Now, to best understand the difference between delta and lambda isomers, it's best to have a molecular model kit and drawing and putting together the octahedral shape, so you can actually see the differences between these two. And it's very much like propeller fans, because one rotates back and to the right, and this is the delta, and the other rotates back and to the left, and this is the lambda. So you can kind of think about the faces on the octahedron. So the delta goes back and to the right, and the lambda goes back and to the left. You can also think about pinwheels or fans or anything that has a propeller-like shape. where they can rotate either to the right or to the left. Delta means to the right and lambda is to the left. Now, to help us understand the bonding in compounds, sometimes we use valence bond theory, and we learned about valence bond theory in Chem 1A.